In this video, I'm gonna compare the second derivative test and the Lagrange multiplier technique for you. And we're gonna do some more example on this one, okay? So the second derivative test, you're gonna see that the question, okay? So let me compare them in this way. So I'm gonna first talk about what kind of question that you're gonna have. So the question that you have is going to be determine it's going to be determine the relative extremum of fxy equal to, and the question will give you the function for fxy. Okay. The second way is going to be this one for the second derivative test is going to be you're going to find the relative extrema of function. However, the Lagrange multiplier, this one is going to be you have constraint relative extrema. Okay, so the difference turn out to be you have constraint or with constraint or without constraint. And the constraint relative extrema, the question turn out to be you're gonna have maximize, minimize, okay, or sometimes it's going to be just optimize. So it's going to be maximize, minimize, or optimize the function fxy, and the question will give you fxy, and it's going to say subjects to constraint gxy equal to 0. So this one is the yellow constraint that we usually have. Okay, so let me erase this one a little bit. Okay. So for constraint, we usually use the yellow one, right? So that's what it's gonna be. So the difference between these two guys is first, you see the question is asks you something different. The step one for the second derivative test will be you're gonna determine the critical point okay by computing, by solving. Okay, so the equation that you're gonna solve for the critical point will be fx equal to 0 and fy equal to 0. Okay, so you're gonna solve for critical point. Okay, so the step one for Lagrange multiplier will be you're gonna form. Okay, so you're gonna form what is called function f x y lambda so it's gonna be f x y lambda equal to f x y plus lambda gxy. Okay, I know that in your books, okay, so I know that in your books you have what is called, you have negative here. However, you can use positive or negative. In my feeling, the positive one will be easier in order to find f lambda. Okay, so in this case, I would suggest you to use positive, different a little bit from the textbook. So this one is step 1, okay? And step 2, okay? Step 2, you're gonna compute the second derivative. So you compute d by finding. So you're gonna find fxx, fyy, and fxy, okay? And you have d equal to fxx, fyy minus fxy squared. And in the third step, okay, so in the third step, you're gonna use the second derivative test to classify the critical point in step 1. So you're gonna have a table, okay? So you're gonna have a critical point, you're gonna have D, you're gonna have fxx, you're gonna have conclusion and value. So you're gonna have the point, okay? So you have D, you have fxx, let me use different color. So you have D, you have fxx, you have the conclusion, and you have the value. Okay, so for the positive, if you have the positive, fxx negative, so this one is going to be relative maximum. If you have the positive, fxx positive, so it's going to be relative minimum. Okay, and if you have the negative, it's going to be saddle point. And if you have the equal to 0, it's going to be inconclusive. Okay, so it's going to be like 4 cases. However, most of the time, you're going to see only 3 cases here. So it's going to be positive, negative, relative maximum. And you have positive, positive is going to be relative minimum. And you have the negative, it's going to be saddle point. Okay, so this one will be classification that you may need to memorize them. So this one is about the second derivative test. However, for Lagrange, the second step is gonna be you're gonna solve for the critical point. So it's gonna be solve for xy from the f lambda equal to just gxy equal to 0, and you have fx equal to 0, fy equal to 0, and most of the time you're gonna solve for lambda, and this guy will be the same, okay? And you're gonna have relationship in x and y. Okay, so this is what you get, and you have equation in x and y, and you're gonna put into gxy equal to 0, and this is what you get. Okay, and the third step for this one, okay, so let me put number 1, okay, so number 1, number 2, and number 3. Okay, so you have number 3 is going to be, you're gonna compute fxy for the point, so it's going to be for every point xy obtained in the second step. Okay, and the highest one will be maximum, and the lowest one will be minimum. Okay, so this one will be the thing that you have. However, sometimes you have only one point. Okay, so if you have only one point, so you read the question. Okay, so if you have only one point, you just read maximum or minimum from the question. So this is how we determine by the method of the Lagrange multiplier. Okay, so this one will be, I compare them for you. You have 3 steps, the same thing as you have for second derivative test and the Lagrange multiplier. Okay, so okay, so let's do some example. So for the first one, you have a manufacturer produce 2 products which demand function Q1 equal to 80 minus 2P1 plus P2 and Q2 equal to 30 plus P1 minus P2. The first question, you like to find the total revenue function. So the total revenue function will be just P1. Okay, so for number 1 here, you have the total revenue function will be P1 Q1 plus P2 Q2. Okay, and for this one will be just P1 80 minus 2P1 plus P2 plus P2 30 plus P1 minus P2. Okay, so this one will be the revenue function. And the question gives you that the cost for producing a unit of product 1 and product 2 are $40 and $30 respectively. We like to express the total cost function as a function in P1 and P2. Okay, so this one, you know the cost for making the quantity. So Q is the quantity, right? So the second one will be 40 Q1 plus 30 Q2. So this will give you the cost in making product 1 and product 2 together. Okay, so you have the cost function, and the cost function given by the function in terms of P. So you would get what is called 40 multiplied with 80 minus 2P1 plus P2 plus 30 minus, not minus, times 30 plus P1 minus P2. Okay, so that's my cost function. And the last one is the profit function. The profit function turned out to be just the revenue subtract by the cost function. Okay, so that will be my profit function. Okay, so for number 4, the question asks you to find the maximum profit. And the question asks you to find the maximum profit without any constraint. Okay, here, so you see that this guy without any constraint. So in this case, you're gonna just use the second derivative test. Okay, so we're gonna use the second derivative test. So in order to use the second derivative test, you're gonna find the derivative with respect to P1 and derivative with respect to P2. Okay, so I'm gonna have the P1. Okay, so it's gonna be P1 and I have P2. So the derivative with respect to P1, derivative with respect to P2, it's kind of difficult to write this thing down. Okay, so you're gonna have derivative with respect to P1. Okay, so for this one, you're gonna have to like expand, or you're gonna be able to differentiate this one. Okay, so for this one, you see that if I have the revenue, okay, so let me find the revenue and the cost function for you in the term that you can differentiate this one quite easy. So for this one, it's gonna be 80 P1 minus 2 P1 square plus P1 P2 plus P1 P2 plus 30 P2 plus P1 P2 minus P2 square. Okay, so that will be the revenue function, and you're gonna subtract by the cost function. So it's gonna be 3,200. Okay, and you have minus 80 P1. Okay, and you're gonna add by 40 P2. Okay, so this one will be inside big parentheses 80, yeah, it's correct, and plus 900, okay, plus 30 P1, okay, and minus 30 P2. So you're gonna differentiate this guy. So you see that it's gonna be 80. Okay, so it's gonna be 80 differentiate with respect P1 minus 4 P1. Okay, so minus 4 P1, and you're gonna have P2 plus P2, P2 plus P2, P2 plus P2, and the rest of the term here. So you have negative minus, so it's going to be plus 80 minus 30. Okay, so this one will be derivative with respect to P1, and derivative with respect to P2 turn out to be, let me differentiate first. So it's gonna be 0, 0. So it's gonna be P1, P1, P1 plus P1 plus 30 minus 4, not so, 2P2, 2P2, okay? And you have minus 40, minus 40 plus 30. Okay, so this one will be derivative with respect to P1 and P2. Okay, and this one after simplification, you would see that this guy will be negative 4p1 plus 2p2, and you have 130. 130 equal to 0. And you have 2p1 minus 2p2, and you have plus 20 equal to 0. Okay, so this allows you to have negative 2p1 plus p2 equal to, I divide by 2, is going to be 65. Actually, I don't need to simplify. I can just sum this one up, right? So this is, when you sum this one up, you're going to get negative 2p1 plus 150 equal to 0. So you would get p1 equal to 75. Okay, so you have p1 equal to 75, and you solve for p2, and you have p2 equal to, what is p2? So p2 will be p1, p2 will be p2 will be p1 plus 10, right? P2 equal to p1 plus 10, so it's gonna be 75 plus 10 equal to 85. Okay, so I have p1 and p2 for the critical point, and then I gonna do what? I gonna do the second derivative. Okay, so I do the second derivative. So I have the p11, okay, p1. So you get negative 4, p1, p22 is gonna be negative 2, and p12 is gonna be 2. So you would get d equal to negative 4, negative 2 minus 2 square. So it's going to be 4, okay, and positive. And you're going to have p11 equal to negative 4, negative. So from here, it's going to be classification to be relative maximum. 75, 85, okay, is a relative maximum, okay, and you'll be able to find the maximum profit by plugging in the value. And the next question is how many, okay, how many unit of product 1 and product 2 should be sold to maximize the profit. So the question asks you to find Q, okay? So Q1, okay? Q1 equal to, okay? Q2 equal to, so we learned that Q1 is 80 minus 2P1, 80 minus 2p1 plus p2, and q2 is equal to 30 plus p1 minus p2. Okay, so this guy will be just 80 minus 2 times 75 plus p2, which is 85. And you have 30 plus 75 minus 85. So it's going to be 20, okay, and 15. Okay, so this one will be the quantity. So it's going to be the product 1, 15 pieces, and Q2, which is the product 2, 20 pieces. Okay, so that one will be the one for this long question. So this one kind of step by step for you. Okay, and this one after reading is going to be maximum without any constraint. So you're gonna just use the second derivative test. The next one, we have a company produces stainless steel for domestic and international market. Okay, and you have the domestic market given by P1 equal to 630 minus 40 Q1, and international market is P2 equal to 800 minus 50 Q2. Okay, and you're gonna have the cost function CQ equal to 20 plus 100Q, and how many tons should the company sell in each market to attain maximum profit? Okay, and what are the corresponding prices per ton? So you like to find the maximum for the product. Okay, so in this case, you like to find the profit function again, and you gonna have the revenue. So you have the revenue in this case. It's gonna be P1 Q1 plus P2 Q2. So you would get just 630 minus 40 Q1, and you have Q1 plus 800 minus 50 Q2 times Q2. Okay, so that's my revenue function. And then you're gonna have the cost function. So the total cost function, how much pieces, how many pieces that you have. So the cost function turned out to be Q1 plus Q2 pieces. Okay, so you need the total cost function. The total cost function turned out to be the cost function when you produce Q1 plus Q2 pieces of your product here. So you have C Q1 plus Q2 is gonna be 220 plus 150 Q1 plus Q2. Okay, so that my revenue, that my revenue and my cost function respectively. So you're gonna have the profit function turn out to be the revenue subtract by the cost function. Okay, and so you're gonna find derivative with respect to the first variable and derivative with respect to the second variable. Okay, so you differentiate with respect to Q1. So here it's going to be 630 minus 80 Q1. Okay, so that take care Q1. And you have minus this guy. So it's going to be 150. Okay, so you find derivative with respect to Q1. Let me make the reading easier by highlighting the variable a little bit. So you have your Q1, you have your Q2, and the next one you get 800 minus 100 Q2 minus 150 equal to 0, equal to 0. Okay, and so you see that you're gonna be able to solve for Q1 and Q2 separately. Okay, so you have Q1 and Q2, and you're gonna compute P11, which is negative 80, P22 equal to negative 100, and P12 equal to 0. Okay, so that will be the derivative. And then you're gonna find D for me, and you're gonna have to use the second derivative test in order to reach the conclusion. Okay, so I will leave this one for you to compute on your own first, and then in the recitation, I will give you the solution. Okay, so I'm gonna give you the complete solution later. The third one, you see that you have the constraint given by a consumer. A consumer is to buy product A and product B at price PA equal to 2, PB equal to $3 per unit with the fixed amount of budget I equal to 48. So this guy will be 2x plus 3y, okay? And the satisfaction function turned out to be uxy equal to x cubed y cubed. And you like to maximize the satisfaction. So you like to maximize the satisfaction. So this one again. So you have maximize subject to the constraint that you buy 48 equal to 2x plus 3y. So in this case, you're gonna have your gxy. So you have gxy equal to 2x plus 3y minus 48 equal to 0. So you're gonna have fxy lambda equal to your satisfaction function plus lambda. Your gxy is 2x plus 3y minus 48. So this one is the yellow function and the pink function respectively. Okay. And then you see that for this one, it's gonna be, you need to compute f lambda, which is 2x plus 3y minus 48, fx and fy. Okay, and you're gonna, so for lambda, and you're gonna have x and y. Let's complete this one. So it's gonna be 3x squared y cubed. And for this guy, it's gonna be x cubed times 3y squared plus 2 lambda plus 3 lambda equal to 0, equal to 0. So you're gonna have lambda equal to, okay, so you get 3 over 2 x squared y cubed, and you're gonna have 3 over 3, so you're gonna get x cubed y squared with the minus sign in front, okay? And then you're gonna have this guy equal to this guy, okay? So from this allows you to conclude that you have 3y equal to 2x, okay? And you're gonna put 3y equal to 2x that you found here into this equation to solve for x and y. And you're gonna get the maximum satisfaction, okay? Okay, I will let you finish this one for me first, and then I'm gonna give you the full solution again at the recitation. Okay, the final one will be, you have an open top rectangular box is to have a volume 6 cubic feet. Okay, so again, you have a rectangular box. So it's gonna be a box. So you get a box like this, and it's gonna be, you have xy, right? So it's gonna be xy, z, okay? And you have the volume equal to x, y, z equal to 6 cubic feet. And the cost per square feet, per square foot of materials is $3 for the bottom. Okay, so you need to see the bottom a little bit. Okay, so for the bottom, it's gonna be $3. So you have $3 per square feet. So the bottom, the area is XY, right? The area is XY and it costs $3. So that's my bottom. And $1 for the front and the back. Okay, and $2. So the front and the back is $1. So it's gonna be here and here. Okay, so the front and the back, front and the back turn out to be my exact times 2, right? So it's gonna be 2 exact. And it's gonna cost me $1. Okay, and the other side is 0.5 and it's gonna be 2YZ. Okay, so we like to find the dimension of the box so that the cost of material is minimized. So in this case, you don't have constraint. Okay, so you don't have constraint in this case. So you gonna just use second derivative test. Okay, so this one is x, y, z equal to 6. Okay, so this allows you to solve for z. So z will be 6 over xy. Okay, and you're gonna plug into the number here. So in this case, the cost function, okay, turn out to be the sum between the red guy, which is 2xz, okay, and you have yz, and you have 3xy, and you have 3xy. Okay, so this one, and this guy will be 2xz, so it's gonna be x 6 over xy plus y and 6 over xy, and you have 3xy. Okay, so this one will be just that. And then what? And then you gonna simplify this one. So this would allow you to have 12 over y plus 6 over x, okay, plus 6 over x plus 3xy, okay, for me. And then you're gonna be able to compute cx and cy. Okay, let's compute cx. It's going to be negative 6 over x squared plus 3y, and you have negative 12 over y squared plus what is called 3x, okay, equal to 0. And you solve for critical number for me here, okay, and then you gonna compute cxx. Cxx is gonna be 6 over, not 6, 18 over x cubed, okay, cxx, cyy, cyy will be negative, so it's gonna be 24 over y cubed, okay, and you have cxy equal to 3. Okay, so you're gonna check for the second derivative. Okay, so for this one will be just you like to find not you like to find, you like to find the minimum, what is called minimum cost, okay, for the material. and you use the second derivative test. Okay, so I let you finish this one, and I will tell you the solution again during the recitation. Okay, so this one is another word problem that you should practice by yourself. Okay, so let's conclude a little bit for this clip. So I talk about the difference between the second derivative test and the Lagrange multiplier, what kind of problem that you can have. And then I give you several examples here that ask you to use the second derivative test, or some question ask you to use the Lagrange multiplier. Okay, so, and I let you do these 3 questions, okay? And during the recitation, I will give you the solution and I will conclude everything for you again. Okay, so that's all for this week on the Lagrange multiplier function.